Okay, we continue to learn Chapter 3, Vector Spaces, and Section 2, Subspaces. Part 2, Span and Spanning Set. First definition for span of a set of vectors. Let V1, V2 till Vn be vectors in a vector space V. A sum of the form alpha1 times V1 plus alpha2 times V2 plus till plus alpha n times Vn, where alpha1, alpha2 till alpha n are scalars, is called a linear combination of a given vectors V1, V2 till Vn. So here, in this form, V1, V2 till Vn are given vectors, where alpha1, alpha2 till alpha n, they are real numbers, they are scalars. The set of all linear combinations of V1, V2 till Vn is called the span of those given vectors. So the span of these vectors be denoted by this form, a span of V1, V2 till Vn. Okay. For example, the null space of A we just computed in section 2 is the span of given two vectors. So the first vector is 1, minus 2, 1, 0, and the second vector is minus 1, 1, 0, 1, because the null space of A at that time we compute is equals, right, alpha times this first vector plus beta times the second vector, where alpha beta can be chosen arbitrarily, so it is a span of these two vectors. And in three-dimensional real vector space, we consider span of E1 and E2, where E1 is the first coordinate vector 1, 0, 0, and E2 is the second coordinate vector 0, 1, 0. And if you do the span, so this is the linear combination of vectors of E1 and E2. So you will get this plane, see, the whole plane of x1 or x2. And if you consider the span of these three coordinate vectors, E1, E2, and E3, where E3 is the vector 0, 0, 1, then the linear combination of these three given vectors can equal any vector in R3. So this span is just the whole space, three-dimensional real vector space. We have this theorem first. If V1, V2 till Vn are elements of a vector space V, then we know that its span is a subspace of V. So this span is a special subspace. Okay. In order to show this, in fact, we first should say this set is non-empty. This set is of course non-empty, right? Because those given vectors are in this span, of course. And then you need to show that for the scalar multiplication and addition, they are closed in this set. We show this. Let beta be a scalar and V written as a linear combination of given vectors V1, V2 till Vn, and W is also a linear combination of these given vectors V1, V2 till Vn with scalars beta 1, beta 2 till beta n. Okay, so there are two elements, arbitrary two elements in this span. Okay, and then we check beta times V, where beta is an arbitrary real number. So beta times V equals this one, beta times alpha 1 times V1 plus till plus beta times alpha n times Vn. Because we write in this form, so we can say beta V is still in the span of given vectors, because we are given vectors V1 till Vn, and you just change the scalars to beta alpha 1 till beta alpha n. So beta V also in this span. And you can show also V plus W. V plus W you can write as this form, also linear combination of given vectors V1 till Vn, with the scalars now becomes alpha 1 plus beta 1 till alpha n plus beta n. So this summation V plus W also in span. So this means the scalar multiplication and addition are closed in this set span. So this span is a subspace of V. We show this. Okay. Now let's look at some geometrical interpretation. Span of E1, E2 in R3 is just the x1 or x2 plane. just this plane. And if you have arbitrary two vectors x, y, which are not collinear, which are not in the same direction, in the same line, okay, then you know that span of x and y, this is a plane determined by x and y. So given you two vectors here, x and y, then you do the span. This will be the plane passing through these two vectors. Okay. Now we have another concept about a spanning set for a vector space. So what is a spanning set? Let V1, V2 till Vn be vectors in a vector space V, and the span of V1 till Vn is a subspace of V, spanned by these given vectors. It may happen that the span just equals the whole space V. In this case, we see that the vectors V1, V2 till Vn span the whole set V, and the vectors, the set of given vectors V1, V2 till Vn is a spanning set for V. So the spanning set means these vectors can span the whole space. So it is a spanning set. Now we give this definition. The set V1, V2 till Vn is a spanning set for V if and only if every vector of V can be written as a linear combination of V1, V2 till Vn. So this is a definition for the spanning set. Any vector can be written as a linear combination of these given vectors. So these given vectors are enough to represent the whole space using the scalar multiplication and addition. Now we see these examples for spanning set. Okay, the problem is that ask you to determine which of the following are spanning set of R3. So this means which of the following can span the whole set. Okay, so see, the first set of vectors contains E1, E2, E3, and this vector 1, 2, 3, this vector. Of course, because E1, E2, E3, if you span these three vectors, it can be the whole space of R3, right? So, of course, if you add additional one, it is also a spanning set of R3. How about the second set of vectors? So here is 1, 1, 1, here is 1, 1, 0, here is 1, 0, 0. So this one is also a spanning set of R3. You can consider like if you can express arbitrary vector in R3, for example, x1, x2, x3 as a linear combination of these three vectors equals alpha times 1, 1, 1 plus beta times 1, 1, 0 plus gamma times 1, 0, 0. And you can find that this system is consistent. So this is a spanning set of R3. Okay, now we see the third set of given vectors. So the first vector is 1, 0, 1, and the second vector is 0, 1, 0. So now, if we do the linear combination of these two given vectors, you can find that for such vector, the first component and the third component must be same, right? Must be alpha, beta, alpha in this form. Of course, in R3, you have other vectors where the first and third components, they are not equal. So this linear combination cannot be a spanning set of R3, right? And now we see the fourth set, this set of three vectors. And then you should also check whether an arbitrary vector x1, x2, x3 can be written as a linear combination of these three given vectors equals alpha times 1, 2, 4 plus beta times 2, 1, 3 plus gamma times 4 minus 1, 1. And using the Gaussian elimination way for the augmented matrix, you can find that this system may not have a solution for special x equals x1, x2, x3. So you can show that this set is not a spanning set for R3. Okay, and for the vector space in the functional space, right? P3, this P3. If these three vectors in P3 can span the whole space P3, So P3 means the set contains all the polynomial functions with degree less than 3, smaller than 3. Okay, so you can check. Here we have 1 minus x power 2, and here is x plus 2, and here is x power 2. So we have, if we use the first polynomial function, add the third polynomial function, you will get 1, right? You will get 1, so it's the constant term. And for the order 1 term, x plus 2 can provide us x, right? And here is you also have x power 2 term. So the linear combination of these 3 terms can really give you arbitrary polynomial function with degree less than 2. So this is a spanning set of P3.